Have you ever gazed at the stars and dreamed of humanity living among them? Imagine a future where distant planets are not just points of light, but new homes. This isn't just science fiction anymore. The silent, tireless force poised to make this a reality is artificial intelligence. AI is not merely assisting, it's revolutionizing space exploration, particularly in the mapping and colonization of planets, potentially preceding human missions and laying the very groundwork for our expansion into the cosmos. For centuries, humanity has looked to the heavens with wonder. Now, with AI, we're not just looking, we're reaching out with unprecedented capability. AI is transforming how we explore, analyze, and understand celestial bodies, making the impossible possible. Think of NASA's Mars rovers, Curiosity and Perseverance. These aren't just remote-controlled toys, they are sophisticated AI-powered explorers. Their ability to navigate treacherous Martian terrain independently, analyze conditions, and send critical data back to Earth is a testament to AI's power. AI algorithms, leveraging advanced computer vision and pathfinding, allow these rovers to identify obstacles, plan optimal routes, and even select scientific targets without constant human intervention. This autonomy is crucial for missions where light-speed communication delays make real-time human control impractical. It means faster progress, safer operations, and the ability to explore areas previously deemed too risky or inaccessible. Space missions generate an astronomical amount of data: images, spectral readings, atmospheric compositions, geological surveys. Processing this deluge of information manually would be a monumental, if not impossible, task. This is where AI shines. AI algorithms can process vast datasets in real time, identifying patterns, anomalies, and significant features that might take human scientists years to uncover. From detecting subtle changes in planetary atmospheres to identifying potential exoplanet candidates in telescope data, AI speeds up discoveries exponentially. This rapid analysis reduces human workload, optimizes resource use, and accelerates our understanding of the universe, allowing scientists to focus on interpretation rather than raw data processing. Before we can set foot on a new world, we need to know its contours, its composition, its hazards, and its resources. AI systems are transforming planetary mapping. Using deep learning techniques and artificial neural networks, AI can process orbital imagery, LiDAR data, and radar scans to create incredibly detailed, high-resolution topographical and geological maps. These AI-generated maps are not just pretty pictures. They are multi-layered datasets that highlight elevation changes, rock formations, potential lava tubes, and even subsurface features. This offers a fast, simple, and incredibly precise approach to understanding planetary landforms. These comprehensive geological maps are then indispensable for planning future robotic explorations, identifying safe landing zones for human missions, and pinpointing areas rich in valuable resources. Survival in space, and especially on another planet, hinges on resources. AI is becoming our most effective prospector. AI can analyze spectroscopic data from orbiters and rovers to detect the presence of water ice, crucial minerals, and other vital resources needed for survival and industrial processes. By identifying specific spectral signatures, AI can pinpoint concentrations of elements like iron, titanium, and silicon, or compounds like water, methane, and carbon dioxide. This capability is foundational for in-situ resource utilization, ISRU, the practice of living off the land. AI-driven analysis allows us to prioritize exploration efforts, directing rovers and future human missions to locations where resources are abundant, significantly reducing the need to transport materials from Earth. Beyond exploration, AI is the silent partner in humanity's most ambitious endeavor, establishing permanent outposts beyond Earth. The challenges of building and sustaining life on another planet are immense, but AI offers solutions that were once confined to science fiction. Imagine robots building habitats on Mars or the Moon, entirely on their own. This is the promise of AI in autonomous construction. AI-equipped robots can autonomously assemble structures, repair damages, and perform maintenance, even in the most hazardous and remote environments. They can utilize local materials, such as lunar regolith or Martian soil, combined with advanced 3D printing technologies to create sustainable living spaces, landing pads, and radiation shelters. AI algorithms optimize construction plans, manage material flow, and monitor structural integrity, ensuring efficiency and safety. This capability is critical because transporting building materials from Earth is prohibitively expensive and logistically complex. AI-driven construction means we can build faster, more affordable, and with greater resilience in alien environments. The concept of in situ resource utilization, ISRU, is paramount for sustainable space colonization. AI is the engine that drives it. AI can facilitate the extraction and utilization of local resources, drastically reducing our dependence on Earth. AI-driven robots can identify optimal extraction sites, control mining machinery, and even refine raw materials into usable forms. For instance, AI can manage systems that extract water from lunar ice for drinking, oxygen production, or even rocket fuel. It can oversee the processing of Martian regolith to create building materials or extract metals for manufacturing. By intelligently managing these complex processes, AI makes self-sufficiency in space a tangible goal, transforming barren landscapes into sources of vital supplies. While a long-term and highly speculative concept, the idea of terraforming, altering a planet's environment to make it more Earth-like, would be impossible without advanced AI. AI could manage the incredibly complex atmospheric models required to alter atmospheres, control temperatures, and create nascent ecosystems. Imagine AI-powered drones seeding planets with genetically modified plants designed to thrive in alien conditions, or managing vast systems to extract carbon dioxide and release oxygen. AI would be essential for monitoring the delicate balance of a transforming planet, adjusting parameters, and predicting long-term environmental changes. It's a vision of AI as a planetary engineer, guiding the evolution of a world over centuries. Once habitats are built, they need constant, meticulous management to sustain life. AI is perfectly suited for this. AI can monitor and control every aspect of life support systems, ensuring optimal levels of oxygen, temperature, humidity, and atmospheric pressure. It can detect anomalies, predict equipment failures, and initiate repairs or maintenance protocols autonomously. Furthermore, AI can manage advanced hydroponic or aeroponic systems for growing food in space, precisely adjusting nutrient delivery, lighting conditions, and environmental parameters to maximize crop yields. This intelligent automation ensures the health and well-being of human inhabitants, creating a stable and sustainable living environment far from Earth. The integration of AI into space exploration and colonization offers transformative benefits that are simply unattainable through human-centric approaches alone. AI can make decisions and execute tasks with incredible speed and precision, unburdened by human limitations. Unlike humans, AI systems don't need oxygen, food, or rest. They are immune to the psychological stresses of isolation and confinement. They can survive and operate in extreme environments, from the vacuum of space to the crushing pressures of deep-sea vents, and work non-stop, 24/7. This relentless efficiency means missions can progress at an accelerated pace, gathering more data, performing more experiments, and completing construction projects in a fraction of the time it would take human crews. AI algorithms can analyze vast datasets to optimize mission parameters, from trajectory planning to resource allocation, leading to unprecedented levels of operational efficiency. Space missions are notoriously expensive. AI offers significant avenues for cost reduction. By optimizing mission parameters, AI can reduce fuel consumption, minimize the need for costly human-rated systems, and extend the lifespan of equipment through predictive maintenance. Autonomous operations mean fewer human personnel are required on-site or in mission control, reducing salaries, training, and life support costs. Furthermore, AI's ability to rapidly process data and identify critical information means that scientific discoveries can be made faster, leading to quicker returns on investment and potentially opening new economic opportunities in space. The ability to utilize local resources through ISRU, managed by AI, also drastically cuts down on the astronomical cost of launching materials from Earth. Perhaps the most compelling benefit of AI in space is its ability to significantly reduce risk, especially for human lives. Robots and AI systems can explore areas too hazardous for humans, such as radiation-soaked environments, extreme temperatures, or unstable terrains. They can perform dangerous construction tasks, handle toxic materials, and conduct initial surveys of potentially hostile environments. By sending AI-powered probes and robots as vanguards, we can gather crucial information and prepare environments before risking human lives. This allows us to push the boundaries of exploration further and safer, ensuring that when humans do arrive, the groundwork for their survival and success has already been meticulously laid. As AI's capabilities in space grow, so too do the ethical considerations. These are not just philosophical debates, but practical challenges that must be addressed as we venture further into the cosmos. The increasing autonomy of AI in space raises profound questions. How much control should AI have over new worlds? If AI systems are capable of independent decision-making, could they, in theory, decide to expand without human input, potentially claiming planets or resources for themselves? This isn't about rogue robots in a sci-fi movie, but about the need for robust ethical frameworks and fail-safes. We must design AI with clear objectives, built-in constraints, and mechanisms for human oversight, even in highly autonomous scenarios. The development of ethical AI in space exploration is paramount, ensuring that AI remains a tool for humanity's benefit, not a potential competitor or an uncontrollable force. Establishing clear lines of authority and responsibility for AI systems operating on other planets will be crucial for future governance and international cooperation in space. As AI processes vast amounts of sensitive data, from geological surveys to biological samples, the issues of data privacy and security become critical. How do we ensure that this invaluable information is protected from unauthorized access or manipulation? The potential for cyber attacks on AI systems controlling vital space infrastructure could have catastrophic consequences. Robust cybersecurity measures, encryption protocols, and secure data handling practices must be integrated into every AI-driven space mission. This includes protecting the integrity of scientific data, safeguarding proprietary technologies, and ensuring that the information gathered serves the collective good of humanity. As AI becomes more sophisticated, particularly in its ability to learn, adapt, and even create, e.g., designing new materials or structures, we might eventually face questions about the nature of AI itself. Could advanced AI, operating autonomously for centuries on a distant planet, develop something akin to sentience or self-awareness? While this remains largely in the realm of theoretical discussion, it highlights the long-term ethical considerations of creating increasingly intelligent and independent systems. How would humanity interact with such entities? These are questions that future generations may have to grapple with, underscoring the need for thoughtful, proactive ethical planning in AI development.